Start recording already. So, can you hear me there? I think they can hear. All right. So, we have been discussing about the ionization energy. Ionization ionization energy or ionization potential. So, meaning that we want to make ions from an atom. Atom is neutral. We want to just take one electron off from the atom, and we want to make the ion. And the amount of energy we want to give that atom to make the ion is called the ionization energy, right? So I told you to discuss the ionization energy, the atom should be in gaseous state. Atom should be gaseous state, and also they call the ground state. So previously it should not have taken any energy. So atom must be in the gaseous state and in the ground state. And so you have an atom here, something like this. You have a hydrogen. Let's say hydrogen here. This is a proton, one and one electron here. Now you want to throw this electron completely out of this orbit, and you need to give some energy here. So that amount of energy, so that this is only proton, and the space is left, and the electron is already gone. See that? So this is called, so how much energy you give here, we call the ionization energy. The amount of energy you give to knock out this electron from the outermost orbit is called the ionization energy. Yeah, so that's what we call. Now I give the example there. So the example was, we talk about the potassium. So this is the potassium atom. So if you remember the number of the potassium, what is the atomic number of the potassium? Maybe 19, right? So look the periodic table, potassium is in 19 number. So do the electronic configuration like this. So this is the proton. So proton are 19 there. So 2 electrons are here. This is the first orbit, can hold 2 electrons. And the second orbit can hold 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 to 10. Now I have another 8 electron can go to third orbit. 1, 2, 3, 4, 5, 6, 7, 8. 8 electron go to the third orbit. Now I have one more electron left, and that goes to the fourth orbit. So fourth orbit. See, so this is the potassium atom, right? Now I want to. We are not talking about these electrons at this moment. We just want to. This atom is already in the gaseous state, right? This is in the gaseous state. So I want to throw this electron out from this completely. So I give some amount of energy here, so that this electron absorbs that energy and goes out of that orbit. Yeah, and then it becomes the ion. So when it goes out, there is no electron. So electron is already fly away. So we give the plus sign here. So this is a K plus. So this ion is a K plus, and I give how much amount of energy I give to make this one. That is called the first ionization energy. Make sense? So that number I give you was 419 kilojoule per mole. Meaning that if I have a 6.6023 10 to the power 23 potassium atom in this state, I need to completely throw all the first electron from all this many atoms, I need to give that much energy to that system. Make sense? Kilojoule per mole. It's not. If you have to throw one electron out, you may need a tiny amount of energy. But to throw the electron from this many atoms of this electron, you need a large amount of energy. Yeah. So that's it. Now, this is called the first ionization energy. So how much is the first ionization energy? The first ionization energy to just throw this electron is, I need to give 419 kilojoule of energy for 1 mole of atom. So this electron is already left. Yeah, that electron is already left when I give this much energy. Now, this is called the first ionization energy. First ionization energy, meaning that to remove the first electron, I need to give that much energy. Now, if I want to remove another electron, from where I should remove that electron? From here, right? From here. So you see that already this orbit is already 1, 2, 3, 4, 5, 6, 7, 8, kind of full cell. So it takes a lot of energy to take the electron out from the inner full cell. Yeah. So that's a full cell. So second ionization energy. So second ionization energy, meaning that I need to throw another electron out from here, and this is kind of the full cell. And then to remove this electron, I need to put a lot of energy there, and that amount of energy is 3051 kilojoule per mole. Just the first one I was removing from here, so a small amount of energy, and it's just the electron left, and I need to, if I want to make, throw another electron from here, I need to give a lot of energy because that electron is in inner orbit, and that inner orbit is already kind of full. Yeah, make sense? Good. So that's it. So I told you, take some potassium and put in water. Immediately you will see kind of fire. So it just reacts violently. So that first electron is easily knocked out. But if you want to throw the second electron, it is not easy. So you need to put a lot of energy. And I told you, in chemistry, you never see K2 plus ion. So if you remove this electron out, so you have K plus one charge, right? Now, if you want to make remove this electron and make K2 plus, it's very uncommon. You never see K2 plus ion in any chemistry book. Yeah, you cannot remove the second electron that easily. Okay. So second ionization energy is always higher than the first ionization energy. Yeah. So good. So that I told you. Now let's talk about the periodic trend. So you have a periodic table. So the periodic table is like this. So I have periodic table, this one, and you see a lot of elements here, like this. And let's talk about the second one. So I have a lithium here, beryllium here, and then I have a boron, carbon, nitrogen, something like this. So here is an oxygen, here is a fluorine, here is a neon, like this, right? So periodic table looks like this. I just take that period, and if you go down here, so this is sodium, this is potassium. You can go down the rubidium, cesium. So periodic table look like this, right? So I'm just taking one example. So what happened to the ionization energy if I go from this to this to this to this to this like this? So I already told you, when we go from this to this, the size becomes smaller, right? And the outer electron is pulled by the proton with very strong force, and it's very hard to remove the electron from here. And if you go here, the size of the boron atom is even smaller. The outermost electron is pulled with a great force toward the proton. So it's very hard to remove that outermost electron of boron. Same with the carbon. You go to the nitrogen, even harder. Go to the oxygen, even harder. So you see, so as we go from left to right in the period, the ionization energy increases. So we need to put more and more energy to remove the outermost electron from the atom. Make sense? So the first one was, if you want to throw out the first electron of the lithium, you need to give 513 kilojoule of energy. If you want to throw out the beryllium atom, you need to give 899 kilojoule of energy. That one electron we are talking in the outermost orbit. And if you want to throw the boron, you need to give 801. If you want to throw that first electron out, we need to give 1086 kilojoule of energy. For oxygen, we give 1314 kilojoule of energy. For fluorine, we want to give 1681. And for neon, this is neon 2080. So this number you can periodic table in the slide number 4. So I'm just taking the first row. Yeah, in the slide number 4, first row. So lithium is like this. So lithium has only one electron in the outermost orbit, right? So its size is too big. So I just give a small amount of energy, and it just that electron easily leaves. But beryllium, like small size compared to this one. So the electrons are pulled more tightly toward the nucleus. So it's harder to remove the electrons. So I need to give more energy to remove that electron, 899. If I go to boron, I'll talk about there is some anomaly here. So here is you see the large number, 899, right? You would say, okay, why boron is 801? It should have 900, 899, it should have 950 or something like this, right? It should be more. And it should be and then the nitrogen. I didn't write the nitrogen, I guess. So nitrogen was a 1402. So there are some anomalies. So first of all, we need to see that as we move from left to right in the periodic table, the size becomes smaller. Electrons are pulled more strongly by the protons in the nucleus, and it is hard to remove the outermost orbit electrons. So the ionization energy continuously increases from this way to this way. Now there are some anomalies. Let's look at those anomalies. So sorry, this is 1402. So this is good. So from here to here we go there, and it's good. 899 it increased, right? But as we go from here to here, that decrease. Why it decreased? Why this number is too big? Why this number is too big? So that's called the anomaly. So you go to the there is anomalies in the ionization energy in the sixth slide, and you can look later. So let's look the electronic configuration. So lithium is in number 3, right? So if you do the electronic configuration, you would do something like this: 1s2 to s1, right? This is the 3 electron system, right? So we already talked about this. So you are removing the electron from the this s orbital, and it is not fully filled, right? So it is easier to remove this electron. It's not that stable. Now let's go to the beryllium, and beryllium would be number 4. So that so this is lithium. For beryllium, it is 1s2, 2s2. Now you need to remove the electron from this fully filled s orbital. So it takes a lot of energy if you want to break that electron from the fully filled orbital. Make sense? So in beryllium, the electronic configuration is 2s2, and since this is filled, see, in one orbit we can have maximum of 2 electrons. So it is already fully filled. So it takes very high amount of energy to remove the electron from the fully filled cell. Yeah. So that's why beryllium too much ionization energy. It's not easy to make the beryllium ion. Now let's go to the boron. So if you look the boron, so that's in number 5, I guess, right? 5. So that is 1s2, 2s2, 2p1. So this is the electronic configuration that we discussed previously, right? So 2, 4. So here we are just removing the electron from the p1. So it's not a half filled, it's not fully filled. If it were a half filled, it will be like this, p3. If it is fully filled, it will be like p6, right? So it is easy to remove this p1 electron, because P is neither half filled nor fully filled. So the number of the ionization energy is less here. It's easy to remove the electron if the orbital is not fully filled or not half filled. Yeah. Now let's go to another one. So carbon. So what is the where is the carbon? So this was a 4, 2. Let's look the carbon. Carbon is number 6. So 1s2, 2s2, 2p2. So 2, 4, 6. So carbon is number 6. So this p orbital again is neither half filled nor fully filled, right? So it is easy to remove the carbon electron. So it's not that much high energy. So 1086. Now let's go to the nitrogen here. So you would expect that. So 1084. So maybe here you would be expecting 1100 or 1200, right? But it is too high. 1402 is too high than expectation, right? So why that happens is, let's look the nitrogen. So if I talk about the nitrogen here, this is 1s2, 2s2, 2p3, right? Because nitrogen is number 7, 2, 4, 3, 7, right? Now it's in nitrogen, this p orbital is half filled, right? Because p can have maximum of 6 electrons, but p already has 3 electrons. So it is really hard to remove the electron from the half filled orbital. So it's not easy to make the n plus ion. So it's really hard. Yeah. Why? Because it is we need to remove the electron from the outermost part. So outermost part is already half filled. If it is a half filled, it takes too much energy to remove it. Not easy. Make sense? So this is called the anomalies. So what we are expecting, we are not seeing the trend. Yeah. So that's called the anomalies. Now let's go to look the neon. So if you think that neon has also too high energy needed to remove the electron, so neon is number 10. So neon is in number 10, right? Look the periodic table, it is in number 10. Now to the electronic configuration, 1s2, 2s2, 6, so 2, 4, 6, right? So this is fully filled, right? So it's too hard to remove the electron from the fully filled here. So it also has a very high ionization energy. So they are called the noble gas. So neon, argon, xenon, krypton, so they call radon. So these gases are called the inert gases. Why? Because their outer orbital is like this, 2p6. So they don't want to easily give their electron in the chemical reaction. So they never react during the chemical reaction in chemistry. They may react in the nuclear physics, nuclear chemistry, because they really work with a very high energetic condition. But in chemistry, we don't use the high energetic condition. We just mix it and see what happens, right? So these are we call the inert element in the periodic table because they don't react in the chemical reaction. Why? Because their outermost orbit is already fulfilled like this, so it is not easy to remove their electron. Once we cannot take the electron or cannot remove the electron, they don't react. So reaction meaning that just to lose electron or gain the electron. What is the chemical reaction? Chemical reaction is kind of gaining of electron or losing of electron. If they don't lose electron or gain electron, they are inert. They don't react. Yeah. So they are inert. Inert. INERT, inert. Make sense? So this is the anomaly. So I might give a question like why beryllium has too much ionization energy and it is not like the expected one. You would be saying, okay, in beryllium, the electronic configuration is 1s2, 2s2. So I need to remove the electron from the s orbital, and s orbital, outermost s orbital is already fully filled. So it takes too much energy to remove that electron. Yeah, either look half or look full. Yeah, so in beryllium, we are looking the fully filled. In nitrogen, we are looking the half filled here, like this, right? Yeah, and then in neon also, we are looking the fully filled at 2p6. So those are the anomalies. So they don't normally follow the trend. Yeah, good. So that's the anomaly. Now, what happens if we go from top to bottom? So I told you ionization energy normally increase from going left to right because we have a more effective nuclear charge. The atom becomes smaller. When the atom becomes smaller, it's hard to remove the outermost electron. So ionization energy increases from going left to right. So what happens if we go from top to bottom? So let's look that. So let's look the lithium first. So what is the electronic configuration of the lithium? So that's number 3. So that would be 1s2, 2s1, right? Now I want to remove the electron from the sodium. So if I want to remove the electron from lithium, I need to remove this one, right? 2s1, right? But if I want to remove the electron from sodium, sodium is number 11. So I'm going to write this 1s2, 2s2, 2p6, and 2s. How much is that? 2, 4, 6, 3s1. So like this, right? So that's number 11, right? So I already told you. So I am removing the electron from second orbit here. This is the second orbit in lithium. But in sodium, I am removing the electron from the third orbit. So second orbit is here, and then there are proton, and the third orbit is like this. So this is proton, one orbit. This is second orbit, and then this is third orbit. So is it? So I'm removing the electron from here for the sodium, but I'm removing the electron for lithium from here. So it is attracting with too much force here because this orbit is smaller. So it takes too much energy, right, to remove this one. But I need to remove the electron from here for the sodium. It's too far from the nucleus here, so it is not attracted by that much force. So it is easy to remove the electron. Make sense? So if you go down, in each step, you are adding another layer of the orbit, and then you are putting those electrons, and you need to take that electron out by giving some energy. So it is since the size of this is bigger, the nuclear pull or the pull by the proton is smaller for that electron, and that electron can easily be removed. Yeah. So as we go down from top to bottom, like this, the ionization energy decreases. So lithium has too much, sodium has a little smaller, this has a little smaller. So as you go down, the electron can be easily removed. So there is a rubidium and there is a cesium. So if you put lithium in water, it may not react that violently, but it reacts violently, but it doesn't react violently. But if you put sodium, immediately it catches fire. But with the cesium or the rubidium, even you can put in the air. So if you put those rubidium and cesium, they already reacted gone. So these are really reactive. Why? The outer electron is loosely held, so that electron easily goes to react with something. Yeah. So as you go down, the number becomes the smaller. Ionization energy becomes smaller. Easy to remove the electron. Make sense? Yeah. So just like the ion. So when you go to the laboratory and you just mix something and you say okay plus sodium plus or something, so those are the electrons that can be easily removed. Now I think that's it. Now let's talk about the second ionization energy. So I think there is a second ionization energy here. First and second ionization energy. So I'm still in the fourth slide. So let's look about the lithium. So what is the is number 3. So what is the electronic configuration of the lithium? So this is 1s2, 2s1, right? Yeah. So if I want to now let's talk about the first ionization energy. First ionization energy. I just want to remove this electron, right? First ionization energy. So it is easy to remove this electron. That's the first ionization energy. So first IE is small value. Small value. So that for the lithium that is 513. Small value, that's 513 kilojoule per mole. Yeah. And then now I remove the first electron. Now this is gone, right? Now I want to remove the electron from where? Here, right? Make sense? Now here, this is in the first orbit, and it is already fully filled cell, right? So it takes too much energy to break this cell. Make sense? So second ionization energy, I need to remove from the 1s2, and then this is too big. Why? Previously I was removing from the first orbit, second orbit. If I have to remove another electron, I need to remove from the first orbit, and the first orbit also the s orbital is already fully filled, right? So it takes too much energy to remove the second electron. Make sense? Good. So I already wrote the reason here. You can read in home. Now, second was 7,298. 7,298 kilojoules. Say too much. You might be expecting 530, maybe 700. No, it takes too much energy to remove the second electron of the lithium. So you never see something like this. Everywhere you see Li plus, you never see Li2 plus. So second, it is almost impossible to remove the second electron from the lithium. Yeah, because I need to give that much energy. Make sense? Good. So so from second to third, there is not much higher, because once you remove one, another is easy to remove. So that's okay. So second ionization energy is too big in lithium. Now let's talk about the beryllium. So in beryllium, the electronic configuration is 1s2, 2s2, right? So from where you need to remove the electron? From this one, right? Yeah, so too high, because this I already told you it is a second orbit, and then s orbital is fully filled. So it takes very high amount of energy to remove the electron from the second the fully filled orbital, right? So this, if I have to remove one electron from there, I need to give 899, and it's already high. Now 899. Now this becomes like this. Once I remove one electron, this becomes like this, right? There were two. I already removed one by giving this much energy, and this looks like this. So to remove this one is not that hard. It's a little bit hard, but that is not that hard, right? So this, to remove this one, I need to give about 1757 energy. Now I just remove this one. Now if I want to go to the third ionization energy, I need to remove from here, right? So you see that? Now previously I was removing from the 2s orbital. Now I need to go to the 1s, right? So it takes too much energy to remove the electron from the first orbit and the fully filled. Yeah. So that is the third one. If you want to remove the third electron, 14,848. You see that? So first electron, it is really, it's okay. You can try and you can remove the first electron. But second electron, you don't really have to give that much energy to remove that one. So 809, 1000 to 7, almost a little bit about 700. But if you want to remove the electron from here, then you need to give 14,848 kilojoule of energy. Too much energy it takes. Make sense? So it's easy to remove the electron from the bigger orbit. It is harder to remove the electron from the inner orbit, right? So it's just like this. So the beryllium was like this. I have 2 electron here, this proton here, and then 2 electron. There is a 2 s2 electron, so I can remove this one easily. And since it will experience more force there, a little bit harder to remove this one. But now, if you want to remove this one, too hard, because we need to remove from very close to the proton, right? And then this is already fully filled. So the third, for the beryllium, third ionization energy is too big. But previously, when I talked about the lithium, second ionization energy was too big. Yeah. So like that. Now let's go to look the nitrogen. Nitrogen, I think we already talked about that half filled orbital. So I think it's just like that. So you can just read yourself. Yeah. So if you have to remove the electron from the inner orbit, it takes too much energy. If you have to remove the electron from outer orbit, you can give a tiny bit energy and it just leaves. Yeah. So second, in somewhere, the second orbit has first orbit, second orbit has too much energy. Somewhere the first orbit has too much energy according to the element. So here is a magnesium. So let's talk about the magnesium. So magnesium is, what is the atomic number of magnesium? It's a 12, right? Yeah. Let's talk about the ionization energy. So I'm going to write the electronic configuration: 1s2, 2s2, 2p6, now 3s2. So this is the electronic configuration of the magnesium that we practiced previously, right? Now, first ionization energy, the first ionization energy. How much ionization energy I take to remove one electron? It's pretty easy. So I can remove the first electron pretty easily, and that so I just remove that one from here, and first ionization energy is 738 kilojoule. Just to remove the one, I already removed one, right? So if I want to remove this one, I need to give 1451. So second ionization energy. So that is 1451 kilojoule per mole. Now I already removed this one. Now I need to remove from where? Second orbit, right? Inner orbit. It's too hard to remove that electron now because I already removed from the third orbit. Now I'm going here from third to second, and it's too hard to remove that electron. And if you want to remove this electron from here, there were 6, now it becomes 5. So third ionization energy is too high, 7,732 kilojoule. Yeah. So that's how we explain. Make sense? So I only wrote here, so you can read. Yeah. So anomalies in the ionization energy, I only wrote those, so you can read those there. What else I have here? So I think I repeated one of the slides there, so don't get confused. I think that slide was just repeated when I was copying. So now I'm going to slide number 8 and talk about the electron affinity. Electron affinity. Electron affinity. So here also, it's a kind of energy. So affinity meaning that how you are willing to accept something. Yeah, that means affinity meaning that how much you are willing to accept someone. So that's the affinity. So this is also energy. So we discussed this in terms of energy. So there is an atom. The atom is in a gaseous phase. So atoms must be in gaseous. In ionization energy, also atoms should be in gaseous phase, right? And then this is also in the ground state. Ground state meaning that it has not already absorbed energy and the electron has not gone to the upper orbit. So something like this. So atom is in the gaseous state and is in the ground state. It is how you find in nature. It should be like that. It has not absorbed any energy, right? So you want to put. So let's talk about the lithium here. So this is a lithium, right? Now this is the atom what you find in the nature, like in the periodic table. Now this is in the gaseous state. Gaseous state, and it is in the ground state, meaning the electron has not jumped off already. Now there is an electron coming from somewhere. So there is a lithium here. So this is a proton. That's 3. Lithium is number 3. So there are already 2 electrons here, and then there is another electron here. So lithium is like this, right? Yeah. Hydrogen, helium, lithium. Lithium has a 3 proton and 3 electrons. So I put 2 electrons here, 1 there. Now there is somewhere 1 electron here. Somebody give the 1 electron there, and it's trying to come to this atom here. It's coming from somewhere. So this guy, this is an electron coming from somewhere and want to sit in this orbit. So in that process, if that happens, it releases some energy. So it is coming with a great energy, and when it comes and sits here, so it will have a less amount of energy. Yeah. So some of the amount of energy it is going to lose. It's just like this is the Earth, and there is a large rock coming from here with a great force, right? And then it comes and strikes the Earth here, something like this, and then it loses some energy while it strikes the Earth, right? So something like this. So that amount of energy it releases is called the electron affinity. So it becomes Li. Now it was a neutral. Now it should be negatively charged because it took the negative charge. Now in this process, I told you it releases a lot of energy, some amount of energy, and that is called the electron affinity. Let's talk the energy. So energy. So I give number E, the letter E. So that amount of energy is called the electron affinity. Make sense? Yeah. Sure. Somebody like the electron is just jumping toward the atom, and once it comes to the orbit of that atom, it is going to lose a lot of its own energy and be stable there. Yeah. So that amount of energy released by that electron is called the electron affinity. Yeah. Good. Now here is a chlorine. So lithium, again, making lithium minus is almost impossible. Yeah. So lithium doesn't try to gain electron. It tries to lose the electron. Now here is an example. So chlorine. So they say chlorine, and then this chlorine is already in the gaseous form. This is a chlorine atom, and that atom is in the gaseous form. Yeah. And then they gave 1 electron to this one, and just measure the energy. What happened? How much energy it lost when it goes to attach with the chlorine, and it becomes chlorine minus. It's also in the gaseous phase, and it releases about 349 kilojoule per mole of the energy. So meaning that you have a 6.023 10 to the power 23 chlorine atom in gaseous phase, and you give a lot of electrons from outside, and then those electrons jump and go and attach with the chlorine, and they give the 6.023 10 to the power 23 Cl minus. And what is the energy released in that process? Meaning it becomes hot, right? It releases the energy, and that much amount of energy is called the electron affinity. Make sense? Now this is the energy, but since this energy is the system is giving to us, so we put the negative sign. But in ionization energy, we need to give the energy to the electron so that the electron goes out. So we do the plus sign there. But here we have the chlorine. We have a lot of chlorine atom here, and then from somewhere we are just pumping the electron in, and this system now becomes hot. Now this becomes hot. Why it becomes hot? Because as the electron come and sit with the chlorine, they release the energy, and the whole system becomes hot. Make sense? Therefore, we give the negative number here. Because of this negative number, we get confused a lot in the electron affinity. I was very confused, and I was reading a book this morning, and they say that, oh, because of they give the negative, positive, sometimes this, sometimes that. So when we study about the electron affinity, it is much harder compared to the ionization energy. Just read a book and write that. Yeah. But this is not a negative. Actually, they are releasing this much energy. This was let's say 20 degrees centigrade in the beginning. Now you put the electron there, and the electron go and combine with the chlorine, and after a while you will see measure the temperature in maybe 30 degrees centigrade or 40 degrees centigrade. So it gives out the energy, and the system becomes hot. Make sense? Yeah. So that minus is saying that. So we need to give the minus to the electron affinity. All right. Good. So now look again. So talk about the periodic trend. So what happens? So again, I'm going to write the periodic table here. How does so just like this. So we have this one. So it's like this, right? So we have I just take one, and then so this is I have lithium here, beryllium here, and then I have boron here, carbon here, nitrogen, fluorine, neon. So I have, this is a periodic table, right? And then I have here lithium, sodium, potassium, rubidium. So we need to look how does the electron affinity energy vary. So does it going from here to here to here to here, does it become more, or it become less? Meaning that does this guy want to accept the electron more easily, or this guy want to accept the incoming electron easily, or these are the guys who want to accept the incoming electron easily? I told you affinity meaning that accept easily. Yeah, accept easily. So so this guy doesn't want to accept the electron that easily. So you never see Li minus. You never see Li minus. You look any chemistry book, you never see Li minus. Why? This guy has a very small electron affinity value because it doesn't want to accept the electron. Yeah, it's too big. So we have like this. So if you do the electronic configuration, it is 1s2, 2s1. So this is too big outside. So second orbit can hold 8 electron, but it's already has a 1 electron there. So it is easy to lose 1 electron than to get 7 other electrons to be stable. Yeah. So it tries to lose the electron. So you always see Li plus. You never see Li minus. Yeah. So it tries to lose the electrons. It doesn't want to accept the electron. So electron affinity value for lithium is very small. Now you go this way, and then they try to get gain the electron more easily. It's more for carbon, more for nitrogen, more for fluorine, and there are some they don't want to accept any electron at all. And I will talk the anomalies later. Yeah. So what happens if you go to from left to right in the period? That electron affinity value is going to increase, right? Because the size becomes smaller. The size becomes smaller. As the size becomes smaller, the incoming electron is pulled more strongly by the protons. Yeah, just the size. Or you can talk about the effective nuclear charge also. So you can talk about lithium and boron. So compared to lithium, boron has a more nuclear charge, effective nuclear charge. So the boron atom try to attract that incoming electron with great force and release a lot of energy there. Make sense? Yeah. Good. So as you go from left to right, the electron affinity value tend to increase. Yeah, they try to accept the electron. They are electron hungry kind of thing. So if you go here, fluorine. So fluorine has a 9. So if you do the electron configuration, 1s2, 2s2, 2p5. So this is the fluorine electronic configuration, right? So how many electron does fluorine need to be stable, to be fully filled? One more. 2p5. They want to be 2p6. The p orbital can hold maximum of 6 electrons. So they try to be 6. So they are electron hungry. So they are looking for the electron always. So they have the large electron affinity value. Make sense? So electron. So lithium is not looking for electron. It doesn't like to take electron, but this fluorine is electron hungry. So they want to take a lot of electron very fast, very fast. So why? Because they are P5 configuration. So they want to be P6 and be stable and sit doing nothing. Make sense? Yeah, either way, you can just you can see either this way, or you can see where if I go to from left to right, the size becomes smaller, and the neutron is the nuclear charge is trying to attract the electron from outside more, so they have the more affinity for the electron. You can see something like that, or you can do electronic configuration here, and okay, I have the 2p5 in the outermost orbit of the fluorine, so it is looking for one electron to be stable, so it is always trying to find one electron, so it has a large electron affinity value. Yeah. But if you go to the here in the lithium, lithium has just one electron, so it doesn't want to take the extra electron to be here. So it is easy to lose the electron for lithium than gain the electron. Yeah. So the value for the lithium is small. This way is bigger. The anomalies I didn't talk it. So you can go there in the 9th slide there, and then there is a table here. There is a small table I pulled from the internet. So. We'll see. So let's go from the lithium to sodium to potassium to rubidium to cesium. So what happens if we go from top to bottom in a group? Do they like to have more electron, or they just hate to have more electron, right? So this one, look, the electronic configuration. So this is 1s2, 2s1. So this one is 1, so this is 11, so this is 11, this is 3, so this is 11, so that is 1s2, 2s2, 2s2, 2p6, and 3s1. See that? Now if you go here, that is a 19, so everything is same, 1s2, 2s2, 2p6, 3, I don't know, 3, 19, 2 to 4, 10, so after 2p6 comes to 3s2, and then 3p6 and 4s, how many? 2 to 4, 10, 12, 18, 1. So this looks like this, right? So that's how we practiced previously, right? The electronic configuration. So now, is it easy to add electron here, or is it easy to add electron here? Which one is easier to add the electron? This is too big, so this guy has the electron, so like this. So this one, the electron is here, the outermost orbit is here, there is one electron, and some 19 proton are sitting here. So it's too far, this electron is too far, right? So if electron is coming from outside, this proton really cannot attract this incoming electron here. Too far, this place is too far, right? The size is too big. But the lithium is like this. So lithium is small in size. So you have a lithium. So 3 proton here. So 2 electron here, and then 1 electron is outside here. And if another electron is coming from here, this proton can influence more this incoming electron here. So it is easy to accept this electron for lithium than the potassium here. The potassium doesn't, because this electron is too far from the nucleus, so the potassium atom doesn't want to accept this incoming electron. So electron affinity value for potassium is very small, lithium is larger. Yeah, makes sense. So look, the first one in the slide number 9, the hydrogen has 73. So if the hydrogen is already in the ground state like this, this is hydrogen, so proton is 1, so it's electron hungry. So what it does is, if somewhere there, if it tries to find the electron, so it tries to gain that electron here. Yeah, it tries to gain electron. So it is so if it releases more energy, and that is a 73. So if this electron comes and sit here, it can release 73 kilojoule of energy. Now look, the lithium. Lithium has 60. So this is minus meaning nothing. So minus meaning that they are just releasing that energy. Yeah, minus meaning that energy is being lost, released. Now look, the lithium. So in lithium, so you have lithium here. So 3 proton, 3 proton. So 2 electron here, 1 electron here. So the value for the electron affinity for lithium is 60. So the hydrogen in the top was 73, but it is 60. So this electron, if electron is coming from outside, this lithium is not willing to take this electron compared to this hydrogen. Yeah. So hydrogen was willing to take that electron if electron is incoming from somewhere, but lithium is not willing to take that electron. It may take, but it is not willing. Yeah, kind of that. Yeah, good. Now let's go to sodium. So now let's see sodium. Sodium has, so I already talked about hydrogen. So if hydrogen has to take electron, it would release 23 kilojoule. So if you would talk about the lithium, it only release 60 kilojoule. So it is not trying to accept the electron. So it is trying to, oh, I don't need electron. I don't need electron. Yeah. So lithium is more is like the hating the electron. Now let's go to the sodium, and in sodium you see 53. So sodium doesn't want to take electrons. So lithium, he is trying to take some electron. If there is something, I might take some electron. He's saying something like, but sodium, no, I don't need more electron. Why? Because the electron, it has to put in all the way far orbit. So the nuclear charge is not being able to pull that incoming electron, right? So you see how the electron affinity value is decreasing. Now potassium. So maybe sodium would take some electron if there is a chance, but potassium, no, it doesn't want to take electron. So it's even smaller. Now go to the rubidium. Rubidium is the least one. So rubidium doesn't want to take any electron at all. Yeah. So it is easy to remove the electron from the rubidium, and rubidium doesn't want to accept the incoming electron. Yeah. So these things are opposite. So if you want to remove the electron, remove electron means what? Ionization, right? Ionization energy. Accept electron means what? Accept electron means that electron affinity. So it's kind of playing the opposite thing. Ionization energy and electron affinity are kind of opposite things. Yeah? Make sense? So just to read those, there's a pretty simple language, so you can read a couple of times and you'll understand. Now, what else here? So what happens if we go from this way to this way? So it's one or the other way. So if you go from top to bottom in a group, the electron affinity is going to decrease. So they don't want to take the incoming electron. But if you go from left to right, so these guys here are the electron hungry. So they are always trying to have the electron and release large amount of energy. Yeah, makes sense? So going from left to right in a period, electron affinity increases. Going from top to bottom in a group, electron affinity decreases. Good. Now, this is called the periodic chain. Now, let's look a couple of things here, like the anomalies. So, again, the anomalies are here. The group 7 element has too high electron affinity. So, group 7 element, go to the group 7 element. So oxygen is, look at the oxygen, there is only 141. So if oxygen has to take the electron, it releases about 141 kilojoule of energy. It's pretty small. But if you go to the fluorine, so fluorine has 320, too big. Going from oxygen to fluorine, the electron affinity value is too big. So oxygen doesn't want to take the electron. It's not happy to take the electron. But this guy is really happy. If there is a possibility of finding electron, it really wants to attract that electron, right? Why? Because now look the electron configuration. This is number 8. So 1s2, 2s2, 2p5. So this is this one. Now no, this is 2p4. So it's 8. Number 8. Oxygen is number 8, right? Look the periodic table, and this is number of electron and number of proton in oxygen is 8. Now go here, the fluorine. Fluorine is number 9, atomic number 9. Now do the electronic configuration: 1s2, 2s2, 2p5. Now you see that. So this is trying to be. So this is a tiny bit less than satisfied, right? So it can have a 2p6, but it has 5. So it is very desperate to have one more electron to make it 6 and be stable. Make sense? So this guy is really looking the another electron. Where I can find this electron and I can have. So this is very electron hungry compared to oxygen. Why? Because in oxygen you have a 2p4. So even if you take one electron, it's not going to be fully filled. But here, if you take one electron, it's going to be fully filled. So this is more prone to attract the incoming electron. So this has a very high electron affinity value. Make sense? Yeah. So this is the anomaly. Now, what else here? So one more. All right, so I think we will finish in next class. Yeah, just read there I what I wrote, and I think you will understand. So there is only one thing I just wanted to discuss, but it's fine. All right, so.